Now I will explain how to obtain the solution by using the green function. Now let us consider one example. Suppose the current density has this form. There is a coefficient alpha and the current value is I. We regard it as a function of time. The source exists only at one position, x equals x0, and it is very thin. In other words, it is localized at one point in the x direction. If we draw the geometry, we have the x-axis, and the other two directions are y and z. At x equals x0, a current flows in the z direction. Moreover, it is uniform in the y and z directions, so this represents a current sheet. For x greater than x0, the electromagnetic wave propagates in the plus x direction. For x less than x0, it propagates in the minus x direction. Let us now find the vector potential and also the electric field for this current source. We express the time-dependent current I of t by its Fourier transform, I of omega. Since no specific waveform is given for I of t, I of omega is simply the Fourier spectrum of that current. Substituting this source into the Helmholtz equation, we obtain this equation. To find A sub z, compare it with the green function equation. If we set x prime equal to x0 and attach the appropriate coefficient, it becomes exactly the same form. Therefore, A sub z is obtained immediately. We may also substitute the source directly into the integral formula. Then we replace x by x prime in the green function and integrate with respect to x prime. Because of the delta function, the integral simply picks out the value at x prime equals x0. So we obtain the same result. In this way, we have obtained the z component of the vector potential. The electric field is also easy to calculate. Since the scalar potential is 0, we have E sub z equals minus j omega A sub z. So the answer is simply obtained by multiplying A sub z by minus j omega. Let us simplify the expression a little. The quantity k that appears here is the wave number of the electromagnetic wave. For a wave of angular frequency omega, it is given by omega times square root of epsilon mu. We also introduce the quantity z, called the wave impedance. It is defined by the square root of mu over epsilon. Using this notation, E sub z can be written in a simpler form. So, in the frequency domain, we have obtained the electric field by using the green function. The form is different in the two regions, x less than x0 and x0 less than x. The difference is only the sign and the exponential. This already gives the solution in the frequency domain. However, this time I would like to find the solution in the time domain, not in terms of the frequency spectrum omega. So let us take the inverse Fourier transform. First, consider the region x less than x0. We simply substitute the expression into the inverse Fourier transform formula. The current I is a function of omega because it is the Fourier transform of I of t. Also, k is equal to omega times square root of epsilon mu, so k is also a function of omega, and therefore it cannot be taken out of the integral. For the inverse transform, we multiply by 1 over 2 pi and exponential of j omega t, and integrate from minus infinity to infinity. Combining the exponential terms, we obtain this expression. Now let us denote the quantity inside the parentheses by t prime. Then the integral becomes very simple. Please recall that from the ordinary inverse Fourier transform formula, if we inverse transform the current spectrum I of omega, we naturally obtain the time domain current I of t. Here the integral is exactly the same, except that t is replaced by t prime. Therefore, the inverse transform is immediate. We simply replace t by t prime and obtain the result. Returning from t prime to the original variables, we get this expression. Here, I rewrite the notation by using 1 over c, where c is represented by this equation, and this is the propagation speed of the electromagnetic wave in the medium. In the same way, for the region x0 less than x, we obtain the time domain electric field by inverse Fourier transform. The result is almost the same. The only difference is the sign in that term. Now we have obtained the time domain solution as given by this equation. The physical meaning of this result becomes clear. The source current I of t is located at x equals x0. It emits an electromagnetic wave. The electric field observed at position x appears after a delay. That delay is the distance from x0 to x divided by c. So, apart from the constant coefficient, the electric field has almost exactly the same waveform as the source current, but delayed by the propagation time. The distance from the source to the observation point is the absolute value of x minus x0. The time delay is the distance divided by c, which means the propagation speed is c.